A coronal mass ejection is a massive burst of gas and magnetic field arising from the solar corona and being released into the solar wind, as observed in a coronagraph. Coronal mass ejections are often associated with other forms of solar activity, most notably solar flares or filament eruptions. But a broadly accepted theoretical understanding of these relationships has not been established. CMEs most often originate from active regions on the Sun's surface, such as groupings of sunspots associated with frequent flares. Near solar maximas, the Sun produces about 3 CMEs every day, whereas near solar minima, there is about 1 CME every 5 days. Description: coronal mass ejections release huge quantities of matter and electromagnetic radiation into space above the Sun's surface, either near the corona, or farther into the planet's system, or beyond. The ejected material is a plasma consisting primarily of electrons and protons. While solar flares are very fast, CMEs are relatively slow. Coronal mass ejections are associated with enormous changes and disturbances in the coronal magnetic field. They are usually observed with a white light coronagraph. Cause: recent scientific research has shown that the phenomenon of magnetic reconnection is closely associated with CMEs and solar flares. Magnetic reconnection is the name given, within magnetohydrodynamic theory, to the rearrangement of magnetic field lines when two oppositely directed magnetic fields are brought together. This rearrangement is accompanied with a sudden release of energy stored in the original stressed magnetic fields. On the Sun, magnetic reconnection may happen on solar arcades, a series of closely occurring loops of magnetic lines of force. These lines of force quickly reconnect into a low arcade of loops, leaving a helix of magnetic field unconnected to the rest of the arcade. The sudden release of energy during this process causes the solar flare and ejects the CME. The helical magnetic field and the material that it contains may violently expand outwards, forming a CME. This also explains why CMEs and solar flares typically erupt from what are known as the active regions on the Sun, where magnetic fields are much stronger on average. Impact on Earth: when the ejection is directed towards Earth and reaches it as an interplanetary CME, the shock wave of the traveling mass of solar energetic particles causes a geomagnetic storm that may disrupt Earth's magnetosphere, compressing it on the day side and extending the night side magnetic tail. When the magnetosphere reconnects on the night side, it releases power on the order of terawatt scale, which is directed back toward Earth's upper atmosphere. Solar energetic particles can cause particularly strong aurora in large regions around Earth's magnetic poles. These are also known as the northern lights in the northern hemisphere, and the southern lights in the southern hemisphere. Coronal mass ejections, along with solar flares of other origin, can disrupt radio transmissions and cause damage to satellites and electrical transmission line facilities, resulting in potentially massive and long-lasting power outages. Humans at high altitudes, as in airplanes or space stations, risk exposure to relatively intense cosmic rays. The energy absorbed by astronauts is not reduced by a typical spacecraft shield design, and, if any protection is provided, it would result from changes in the microscopic and homogeneity of the energy absorption events. Physical properties: a typical coronal mass ejection may have any or all of 3 distinctive features: a cavity of low electron density, a dense core, and a bright leading edge. Most ejections originate from active regions on the Sun's surface, such as groupings of sunspots associated with frequent flares. These regions have closed magnetic field lines, in which the magnetic field strength is large enough to contain the plasma. These field lines must be broken or weakened for the ejection to escape from the Sun. However, CMEs may also be initiated in quiet surface regions, although in many cases the quiet region was recently active. During solar minimum, CMEs form primarily in the coronal streamer belt near the solar magnetic equator. During solar maximum, they originate from active regions whose latitudinal distribution is more homogeneous. Coronal mass ejections reach velocities between 20 to 3,200 km per second with an average speed of 489 km per second. Based on SOHO, LASCO measurements between 1996 and 2003. These speeds correspond to transit times from the Sun out to the mean radius of Earth's orbit of about 86 days to 13 hours and 3.5 days, respectively. The average mass ejected is 70121600000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 limits, because coronagraph measurements provide only two-dimensional data analysis. The frequency of ejections depends on the phase of the solar cycle, from about 1 every 5th day near the solar minimum to 3.5 per day near the solar maximum. These values are also lower limits because ejections propagating away from Earth can usually not be detected by coronagraphs. Current knowledge of coronal mass ejection kinematics indicates that the ejection starts with an initial pre-acceleration phase characterized by a slow rising motion, followed by a period of rapid acceleration away from the Sun until a near-constant velocity is reached. Some balloon CMEs, usually the slowest ones, lack this three-stage evolution, instead accelerating slowly and continuously throughout their flight. Even for CMEs with a well-defined acceleration stage, the pre-acceleration stage is often absent, or perhaps unobservable. Association with other solar phenomena. Coronal mass ejections are often associated with other forms of solar activity, most notably solar flares, eruptive prominence and X-ray sigmoids, coronal dimming, Morton waves, coronal waves, post-eruptive arcades. The association of a CME with some of those phenomena is common but not fully understood. For such events no flare could be detected. Most weak flares do not have associated CMEs, most powerful ones do. Some CMEs occur without any flare-like manifestation, but these are the weaker and slower ones. It is now thought that CMEs and associated flares are caused by a common event. In general, all of these events are thought to be the result of a large-scale restructuring of the magnetic field. The presence or absence of a CME during one of these restructures would reflect the coronal environment of the process. Theoretical models. It was first postulated that CMEs might be driven by the heat of an explosive flare. However, it soon became apparent that many CMEs were not associated with flares, and that even those that were often started before the flare. Because CMEs are initiated in the solar corona, their energy source must be magnetic. Because the energy of CMEs is so high, it is unlikely that their energy could be directly driven by emerging magnetic fields in the photosphere. Therefore, most models of CMEs assume that the energy is stored up in the coronal magnetic field over a long period of time and then suddenly released by some instability or a loss of equilibrium in the field. There is still no consensus on which of these release mechanisms is correct, and observations are not currently able to constrain these models very well. These same considerations apply equally well to solar flares, but the observable signatures of these phenomena differ. Interplanetary CMEs. CMEs typically reach Earth 1 to 5 days after leaving the Sun. During their propagation, CMEs interact with the solar wind and the interplanetary magnetic field. As a consequence, slow CMEs are accelerated toward the speed of the solar wind and fast CMEs are decelerated toward the speed of the solar wind. CMEs faster than about 500 km per second eventually drive a shock wave. This happens when the speed of the CME in the frame of reference moving with the solar wind is faster than the local fast magnetosonic speed. Such shocks have been observed directly by coronagraphs in the corona, and are related to type 2 radio bursts. They are thought to form sometimes as low as 2 Rs. They are also closely linked with the acceleration of solar energetic particles. Related solar observation missions. NASA mission Wind. On 1 November 1994, NASA launched the WIND spacecraft as a solar wind monitor to orbit Earth's L1 Lagrange point as the interplanetary component of the global geospace science program within the International Solar Terrestrial Physics Program. The spacecraft is a spin-axis stabilized satellite that carries 8 instruments measuring solar wind particles from thermal to greater than MeV energies, electromagnetic radiation from DC to 13 MHz radio waves, and gamma rays. Though the WIND spacecraft is over 2 decades old, it still provides the highest time, angular, and energy resolution of any of the solar wind monitors. It continues to produce relevant research as its data has contributed to over 150 publications since 2008 alone. NASA mission Stereo. On 25 October 2006, NASA launched Stereo, 2 near-identical spacecraft which from widely separated points in their orbits are able to produce the first stereoscopic images of CMEs and other solar activity measurements. The spacecraft orbit the Sun at distances similar to that of Earth, with one slightly ahead of Earth and the other trailing. Their separation gradually increased so that after 4 years they were almost diametrically opposite each other in orbit. History first traces the largest recorded geomagnetic perturbation, resulting presumably from a CME. Coincided with the first observed solar flare on 1 September 1859, and is now referred to as the Carrington event, or the solar storm of 1859. The flare and the associated sunspots were visible to the naked eye, and the flare was independently observed by English astronomers R. C. Carrington and R. Hodgson. The geomagnetic storm was observed with the recording magnetographic Kew Gardens. The same instrument recorded a crochet, an instantaneous perturbation of Earth's ionosphere by ionizing soft X-rays. This could not easily be understood at the time because it predated the discovery of X-rays by Röntgen and the recognition of the ionosphere by Kennelly and Heaviside. The storm took down parts of the recently created U.S. telegraph network, starting fires and shocking some telegraph operators. First clear detections. The first detection of a CME as such was made on 14 December 1971, by R. Toozy of the Naval Research Laboratory using the 7th Orbiting Solar Observatory. The discovery image was collected on a secondary electron conduction vidicon tube, transferred to the instrument computer after being digitized to 7 bits. Then it was compressed using a simple run-length encoding scheme and sent down to the ground at 200 bits per second. A full, uncompressed image would take 44 minutes to send down to the ground. The telemetry was sent to ground support equipment which built up the image onto Polaroid print. David Roberts, an electronics technician working for NRL who had been responsible for the testing of the SEC Vidicon camera, was in charge of day-to-day operations. He thought that his camera had failed because certain areas of the image were much brighter than normal. But on the next image the bright area had moved away from the sun and he immediately recognized this as being unusual and took it to his supervisor, Dr. Gwenta Bruckner, and then to the solar physics branch head, Dr. Toozy. Earlier observations of coronal transients or even phenomena observed visually during solar eclipses are now understood as essentially the same thing. Recent events: on the 1st of August 2010, during solar cycle 24, scientists at the Harvard-Smithsonian Center for Astrophysics observed a series of 4 large CMEs emanating from the Earth-facing hemisphere of the Sun. The initial CME was generated by an eruption on the 1st of August that was associated with NOAA active region 1092, which was large enough to be seen without the aid of a solar telescope. The event produced significant aurora on Earth 3 days later. On the 23rd of July 2012, a massive, and potentially damaging, solar superstorm barely missed Earth, according to NASA. There is an estimated 12% chance of a similar event hitting Earth between 2012 and 2022. On the 31st of August 2012, a CME connected with Earth's magnetic environment, or magnetosphere, with a glancing blow causing aurora to appear on the night of the 3rd of September. Geomagnetic storming reached the G2 level on NOAA's Space Weather Prediction Center scale of geomagnetic disturbances.